This particular session today is about unit testing our code. So without any further ado, I'm going to give you a brief overview of how this session is going to look like. I know many of you have already attended some of the previous sessions, so this is going to sound repetitive to you, but I can see a couple of new names as well. So what happens in this session is we have a brief introduction to the topic. So for about 15 minutes, I'll talk to you a little bit about the topic, and today's topic is unit testing code. So I will be talking to you a little bit about why should we test our code, what kind of testing techniques and methodologies exist. And then we move into the practical activity. So for about 1 hour after that, we are going to see how unit testing works in practice. You will be coding along with Aman, who is going to be delivering the practical activity. If you want to, so Aman will be sharing his screen and he will take you through unit testing code. And if you wish so, you can code along with Aman. You should also have done setup. Unfortunately, these sessions are very brief. We don't have time to troubleshoot any installation or setup issues. But if you've attended one of these sessions in the past, you already should be set up. We also have a shared notes document like in the previous sessions. I'm just going to switch to the tab to show you the shared document for today, where you have all the links that are relevant for today's session at the top. We are going to ask you also to sign in a little bit below so we can keep an eye on the numbers. And then basically this shared document is for yourselves and ourselves to keep notes, maybe share some bits and pieces of code or some links and so on. You can bookmark this document and come back to it. It will be available to you after this session as well. Right, so let's talk a little bit about unit testing code. Why should we test our code at all? Surely we know what we are doing. When we are typing our code, we are completely confident and we know what will come out at the end of our code as a result. What is the role of automated testing and how can we automate the tests so we don't have to run them manually every time? What does a unit test look like? And also what is test mocking and where it can be useful for us? So those are kind of the questions that we are going to be trying to answer throughout this session. So what is code testing? So code testing is the process of verifying that your code behaves as expected, and also importantly that it contains to do so as it evolves and changes over time. So code testing is going to try to help us answer a couple of questions. So things like, does the code that we develop work as we expect it to? To what extent can we be confident of the accuracy of results that our software produces? Did we check for all the edge cases? Did we consider what could get wrong or go wrong? And do we test how our code behaves in those situations? And also, can we, and more importantly, others who are using our code or want to build upon our code or use our code, can they verify the correctness of our code for themselves? So why would we do code testing? So you might think that, oh, maybe you have a single script that contains maybe a few tens or few hundreds lines of the code. Surely there is no need to test our code. But as the code base grows, and even if it's only a couple of lines of code, debugging of such code bases become much more difficult. I think there is a claim that there is, I don't know, a bug in every line of the code with a really high percentage. So something like more than 90% of our code contains bugs. And tests can help us pick up these problems before they become a problem during runtime. So while you're executing your code, or during perhaps the production stage of your code, while it's being used maybe by hundreds and hundreds of users. If you have a failing test, it will also help pinpoint where the problem lies. It might not always tell you exactly what the problem is, but it will give you a good indication of where to start digging and debugging. Code testing can pick up unexpected changes in behavior of existing code, which result from some future changes. So perhaps you make a change in some part of the code, which seems completely unrelated to another part of the code, but it actually causes problems and issues with that other part of the code. And tests can help pick up those cases as well. Finally, having our code tested will give us confidence, and also to our users, that our code is correct. It can provide correct results. We won't get into a situation where we publish a research paper with some results that ended up being incorrect, for example, or wrong. And also, when you have tests in your code, they are very useful because they also provide invocation or usage examples for the parts of your code. So when you write tests, you're invoking bits and pieces from your code, some functions, and also these can be used by people who are looking at your code to understand better how your code works and how it can be used. So benefits of code testing. Hopefully I managed to convince you that it's a really good idea to write some tests for the code. But just to summarize, well, tests can help us catch bugs early before we publish that paper with some results then we potentially have to retract. It can ensure that changes do not unintentionally break existing functionality. Code testing is really important for long-term maintainability, so it helps create robust code base that is more easily maintainable in the future. Obviously, it builds confidence in your code for yourself and others. And also it makes collaboration and future updates to the code much easier because there is bigger confidence that we won't break things by adding new features or refactoring something or changing in our code. So having well-defined tests for our software helps ensure that our software works correctly, reliably, and consistently over time. So that's really, really critical. Right, so when you're testing your code, a couple of pieces of terminology. You write a set of tests for your code base, and these tests are collectively known as a test suite. The good thing is that the general principles of testing apply across programming languages. So if you learn well, or you learn general principles of code testing in one programming language, you will have no difficulties applying those principles in other programming languages. Yes, the syntax might differ. The tools and frameworks for testing might be different in different programming languages, but the general principles will hold, and you will be able to switch quickly once you get the gist of code testing. There is also something that is called code coverage. So code coverage is the term we use to tell us how much of our code is being tested, and it goes line by line and checks whether your tests cover a particular line of the code. And it's also useful to gain insight into which parts of code aren't being tested, so you can focus your attention on those parts perhaps. Writing tests can also be very time consuming. So it's almost like you're duplicating your code base. Quite literally, for every function that you have in a code base, you need to write a set of tests. So it might seem quite laborious and time consuming. So if you have to prioritize, you should write tests initially for the most critical parts of the code, and those that deliver the greatest value or involve the most complexity. We understand that it's not possible to have a code coverage or test coverage of 100%. Well, you can, but it might be time consuming. And also, even if you have a passing test suite with 100% code coverage, it still doesn't mean that your code is bug free, because it all depends on what it is that you are testing and how it is that you're testing. So you need to be smart about this as well. Right, so a couple of different levels of testing. So you have your code base. At the lowest level, we do unit testing. So these unit tests, they test small, independent pieces of functionality, for example, specific functions in your code. So you should at least be doing that if you're considering what tests to do. And this is something that we will focus in this session in this session. There is integration testing, which is the next level up from unit testing. It tests bigger blocks of code or modules and how they work together and to make sure that they work as expected. This is in particular important for bigger code bases that contain a couple of files, couple of different modules, and so on. And then you've got system testing, which tests the full system functionality, top level interactions between the inputs to your system and the outputs, how you interact with databases, for example, API, other external systems, and so on. Okay, so that was levels of code testing. We also have different approaches to testing. So one approach is when you know what the expected output of a function or a program is, and then you can test directly and check that given a specific input, the result matches the value or fall within a certain confidence interval. However, in some cases, you won't know the exact output. For example, you're doing some random simulations, and typically you won't know what the exact result is going to be. In this case, we've got this what is called property-based testing, which tests a wide range of inputs to ensure that certain properties or patterns hold true across these properties or input values. And that's the best you can do in these situations. And then, importantly, things that have worked before can stop working after a change. And I've mentioned that a change in one part of the code base can affect something in a completely other part of the code base. So this is why we also do regression testing and why it's important. So regression testing is to use to identify these software regressions over time and then safeguard against this unintended side effect by rechecking existing functionality. So normally, if you have loads of unit tests, rerunning these tests after every change is introduced in the code base can provide a regression testing, because you're running your whole test suite every time you change something to make sure that something you've changed didn't break something else. And this is also important, or it's helped by having these automated tools that can run our test suite for us. For example, continuous integration, which is something we will talk about tomorrow, where you can automatically run a large number of tests every time something is committed to your or pushed to your code base. Okay, so I just want to highlight another testing approach, which is called mocking. So when you're running tests, you're often testing for a specific piece of functionality, but often you depend on external objects or functions, and sometimes you can't really test for how these external objects and functions will behave, because there might be some databases or some APIs or some external services that you can't really invoke loads of tests on for practical issues. So for these reasons, mocking allows us to replace these external dependencies or these external services with kind of mocked objects which behave in the same way or behave in the way that you tell them to behave, and then they create replacements of real objects or systems with their simplified and much more controllable versions. So one example of this is if you have a function that modifies data and writes some data to a file, you can mock the file writing object. So you don't want, for example, you don't want to write to a file system every time you run a file because you don't want to fill up your disk space. So instead of creating and saving an actual file, the mocked file writing object will store the written data, or pretend it will mock the file writing functionality, and then you can check the part of the functionality that modifies the data or cleans the data. So you can focus on testing that testing that functionality of your code and forget about whether the writing is done correctly or not. So you can have a focused test on a specific functionality. Okay, so this is the last slide I've got. I just wanted to highlight some practices that are related to testing. So we've covered some of these topics in the past Byte-sized RSE sessions. So code style and linting are also essential practices in code testing. If you attended one of these sessions, you might have remembered that linting tools automatically check that code adheres to code style guidelines. It can pick up some logical errors in the code. It can improve consistency of the code. So it's an aid to testing in a way. So this is something that you would probably run before running your tests. And then I've mentioned tools like continuous integration, which can further help us enhance and automate our testing practice. So they can automatically run our test suite. They can automatically run linting tools for us every time a code change is introduced into our code base. So make sure to check out materials for these two sessions if you haven't attended the code style and linting, and then the continuous integration we will talk about tomorrow. Okay, so with that, I'm going to hand over to Aman to take us through the unit testing our code practical activity.
Perfect. Thank you so much, Alex. Yep, we'll quickly discuss what we'll do today, and then I'll give an overview and we'll get started with the live coding soon. So I'll just share a couple of slides first, and then we can get to the coding part. If I can find my slides. Okay. I'm hoping my slides are visible. Okay,
Yes.
perfect. So yeah, thanks for joining everyone. And as Alex mentioned, yeah, I can see a few familiar names, a few new names. So welcome to everyone who's joined us. For those who are not familiar with, say, a bite-sized RC session, this is a quick-paced session. As you know, it's only 1.5 hours in total. We have about 40 to 50 minutes of practical. What we'll do today is we'll write and run some unit tests, and then we'll do some live coding. So hopefully everyone has a Python installation and Git that they have access to, and that's what we'll mainly be using. We won't need any extra repositories, but again, if you are working in a environment in a virtual in a virtual environment, that might be helpful. If you feel better using that, then we'll use a repository with an example factorial code, and we'll write tests for that. So what this practically will mean would be first cloning the repository, then adding a unit test, and then run those tests. And then we'll change the implementation and look at the test again and see if they're passing. And if we get time, which might be unlikely, to do the follow along live coding for exceptions. But if we have some time in the end, we'll try to look at some exception testing and how to erase errors. So that's the overview. Just again, as a quick note about like how we do the session, how we do the follow along, is that I'll be sharing my screen and I will be sharing whatever I'm doing, and folks can follow me as they go along. We won't have a lot of time for, say, detailed questions. So if you have questions, please do put them in the chat or in the notes document, and I'll try to get to some of them. If something is critical, Alex and Steve are here, they'll help us, but we won't, again, go into details for everything. It will be quick, and I'll try to keep checkpoints. So let's just do a quick checkpoint, say, about the setup. So we'll use Zoom reactions. We have the green checks and the red crosses, and that's what we use. So if you are planning to participate in the live coding today, and you have your setup configured. If you have Python on your machine and you have Git set up, could you please give us a green tick? And if not, you can give us a red cross. Okay. Just to, okay, I think with this one red cross, just to clarify, if that person does not have the setup but wants to participate, they can remove their red cross. But if they don't want to do the live coding, they can remove it. If you want to participate but don't have the local setup, you could use Replit. But again, we won't be able to go into the details of it. It will give you a virtual environment that you can use online. Okay, so I see 12 green ticks. That's great. Okay. Yeah, let's get started then, without further ado. So first, we'll start with looking at what sort of unit tests are, and like as Alex explained, there's a lot of different kinds of testing. So we have a sample code. I'll share that. Let me look. Just a second. Okay, yeah. So we have a sample code. This is a repository. So I'll paste that in the chat. Alex has pasted that. Thank you. Now, this is the repository we'll be using. This is the code we'll be using today for looking at the tests. So we have this repository with two folders. One is called mymath, one is called tests. And we have this file called factorial.py that we will be looking at to test. And then we have a test file already that will help us do some testing and add tests to that. So how we'll start is first we'll get this on our local machine. So first and foremost, we go to the repository. If we get to the home page, we see this code, we see this green button called code, and we'll clone it onto our local repository. So I will use HTTPS here. You are welcome to use any method you want. This is the simplest if you haven't set up SSH or GitHub CLI, or just for like getting the loop code from GitHub to your local repository. So you click on that, you get this code. Then I'll go to a folder where I want to have this code. So currently, if I do a pwd, which is print working directory, it will show me where I am in my files. So I want to go into the RSE folder, and this is where I want to clone my repository. So I will do a git clone and then paste that URL. So we do the git clone, and now if I do an ls will show me what all is in there, the folder, and the factorial example is what we need there. So if folks are able to clone the repository and see the folder, can you give us a green tick? I will give everyone a couple of seconds. So just to recap, there's the repository in the chat that Alex pasted. She's also pasted the command, which is git clone, and then the URL of the repository. And if you enter that on your terminal to any directory you want locally, and you execute that, you should have the local copy of the repository. Okay, I see green text. If someone needs any help, please type in the chat, as Steve says. And if you are again like not able to do it or are having an error, please feel free to put a red cross. So okay, I'll proceed then, since I see a lot of green text. So once we have cloned this, we will open this code into the terminal. So I will activate my environment. So you are welcome to activate a virtual environment if you prefer, but this should not interact or mess with your system Python. So either or works. It's good practice to have a virtual environment that you use. We've discussed this before, but it is not compulsory. So I have my environment activated, and then if I type Python 3 and -v, I have Python 3.12 that I'm working with today. So folks might be able to do Python and then -V. That might work for you. If that doesn't and you're on Mac, Python 3 would work because Macs have this complicated way of, not complicated way, but basically Python 2 was deprecated not until say a couple of years ago. And until then, they used to point to different Pythons. You can make them the same, but I use the default and we'll use everything with Python 3 today. You can execute Python if that works for you. So for me, it won't execute because I don't have Python 2 and I haven't made my Python command equal to Python 3. But if I do this and enter just Python 3, this will take me into the Python interactive interface. So when I go here, this will show me these 3 arrows. And that means that we are into the prompt for Python. Now, if I enter anything here, I don't think it would take us to the right place. Okay, so I forgot a step here. Let's go back. So currently we are still in the parent folder. So what we'll do is we will do CD and we'll go into factorial example. So here I'm using a tab to complete the path. So when I type FAC, for example, and that's the only unique name, if I enter tab, the bash does the completion for me. I click enter, and now I'm into the factorial example folder. So when I click on ls, I can see those 2 folders that we saw on GitHub. So that my math and tests, those are the 2 folders that we are looking for. I'll do a clear again, and then I'll go into Python. Now I'm in Python 3. So if everyone is able to get into their factorial example folder and get onto the Python prompt, can you give us a green tick? To escape, okay, so Control D is an option that you can use, or I think there is quit and brackets. So if you do quit and brackets, that should do it. And I think I'll just test it. Control D also, yeah, quits it. So you can use either or to escape the Python prompt if you want. But yeah, if you're able to get into the prompt, could you please give us a green tick? And you don't need to quit it yet. We will work in the prompt for a minute and then get to VS Code. Okay, I see green text. So if we look at our code, I'll go to my math and I'll go to factorial.py. Now, so this is a Python function, and to execute it, what we'll do is we'll run this function and calculate the factorial. To run this function as well, we will basically use the syntax we use for external Python libraries. So when we do say imports from certain libraries for matplotlib, for pandas, you might be familiar with those. We'll do a similar import and then we'll run our command. So here we'll do from my math, which is the name of the folder, dot factorial, which is our function, and we'll import factorial. So if you do from my math dot factorial import factorial, it should just run and not give you any strange output. So if you enter that command, that should import the method we need. And then if I do factorial in brackets, I give it a number, it should give us the output as the factorial of that number. So I'll do factorial 3, and we know the factorial of 3 is 6. So we'll use that as our testing. So if everyone is able to, I'll clear the feedback. So if folks have been able to run this successfully, can you give us a green tick again? Okay, I see a few green ticks. I'll give people a minute. Okay, great. So yeah, just to recap, so far what we have done is we have got the code from the GitHub to our local machine. We've entered into that folder where we import the code. You can optionally also activate a virtual environment. And then we've got into the Python prompt and tested that function. So once we've done that, now I will quit Python and I'll come back to my command line. So again, I'm into the command line, I'm into the bash. And what I will do is I will open my VS Code and open the same folder in VS Code. So I've opened the folder in VS Code. I can see, again, the same folders here. And then what I'll also do is I'll open a terminal in VS Code so that we are ready to just use everything from VS Code. So we've discussed this in a previous session, but just so that folks are aware, when we use a terminal, the bash is central to the system. So the terminal we'll see in VS Code will be same as the terminal we see in the system terminal. So these are different instances of the same application, but when I execute the commands, they will execute in a similar way. So here we can see I am on factorial example. This is my main branch, and I am on this virtual environment. In VS Code, I haven't activated my virtual environment yet. So I'll do that again quickly. Conda activate. Okay, so we have now a similar setup on VS Code that we had on our terminal. And now we will look at our files. So I'll open the factorial.py and the test factorial.py. So these are the two files we're working with today. So this is our first file, and this is our second file. I am hoping everyone is able to comfortably see the screen. Let me know if it's too small or too big. Now, once you've done that, and you're able to get everything running into VS Code and get everything like set up for yourself, can you give us a green tick again? Okay, perfect. So now what we'll do is, now that we are in the same folder, we will try to run this unit test. So the test factorial.py, which is in the tests folder, is a unit test that we have. And I'll explain the test, but first we'll run it and see how the tests are executed or what information does it give us. So I do a Python -m unit test. So unit test is the command that we're using to execute the default Python testing. So unit test framework is a part of Python. You might have heard of PyTest if you've come across Python testing before, but this is inbuilt into Python, so we'll use this today. And the syntax that we'll use is very similar for PyTest as well. So if you want to extend the syntax in Python unit testing, this should work across testing frameworks usually. So we'll do Python -m unit test, and then we'll do tests. So that's our directory. And then I'll autocomplete it and run the test factorial.py. This is basically what I did here is I'm selecting that file, test factorial.py, and I'm executing it using unit test. That's the framework in Python. Now, when I type this command, it should run everything that is in that file. Now let's hit enter. Ooh, so okay, I can't use Python here. I will go back and I will switch this to Python 3. As I mentioned earlier, Python won't run for me. Python 3 should give us the intended output. Okay, so if I do Python 3, you can do Python 3, whichever, however your system is set up for Python, and then run this file. You should get this output, which says ran one test in 0 seconds and an OK return. So if you get the same output, could you give us a green tick? Okay, I see a red cross. I'll give people a second. Just to clarify, yeah, I'm just seeing in the chat. Yeah, apologies. So the RSE 25, that's just my local repository, my local folder. That's not necessarily what you would name it. You can name it anything. That's just how I refer to it as my local directory. And again, just yeah, I could not get the default bash to work. So this command prompt is also modified. This is just to have a quick look on, oh, this is the branch I'm in. This is the environment I've activated. This is not necessarily how it will look for you. Let me just quickly show you. So your command line could look something like this, which would just be a bash terminal and a $sign or another sign. And yeah, however you've modified it or something similar, but it does not have to show all that information. That is just my personal customization. It can look different for everyone, but it is executing the same commands on bash. So I see a few green ticks. Okay. Has everyone been able to copy that? Module not found. Okay, so that is a good error to look at. So when we have the command, okay, could you also paste the output of your PWD if you do a print working directory? Now, I'm suspecting the error here could be that you are not in the parent directory. So when I do a PWD, I should be in the factorial example. Ooh, okay, so you are in the correct one. Python M unit test tests. Ah, let's debug this. Okay, let me look at my command. So the command is same. Alex or Steve, do you have any inputs on this? Why might we not be able to see the module?
That's interesting. If they're already in the factorial example directory, they should be able to see it, and it looks correct. The command does look correct.
Hmm,
I'm just looking into it now to see if there's another issue that
right.
could be related to this that's causing it.
Okay. I will carry on forward. Is anyone else facing that issue? If you could give us a red cross, if there are multiple people facing that issue. And I think we can debug in the chat as we go. So it might just be like, yeah, it might be an example of some missing character or some missing library. Sometimes the setup is not exactly the same. The directory looks okay, so I'm not sure what's going on. So let's see. If I run this, it gives me this. And if I run my PWD, it's again giving me the same repository. And again, if I would suggest, like, if you just verify that the code looks similar for you, and everything else is similar if there's been a change or Python is importing something different. But moving on if you're able to get this test running, I'll clear my terminal prompt. Now, what happens here is, if we look at this class, what we're doing here is testing the factorial function. So we create a class in Python. Sorry, we're creating a class in Python and we are calling it test factorial functions. And then we use the unit test framework. So we've imported this on the top that is available in default Python. And we give it a test case, and then we test for the case for 3. So we test the 3 factorial. And since we know the output of 3 factorial, that should be 6. It gives us the test ran OK output. So it tests this output, it inputs 3 into the function and tests it against the output that is expected, that we have told it is 6. Now unit test is built in, and you can use PyTest as well. Now we run the unit test using Python M unit tests, and then we give it the file name containing the tests that begin, the test file basically. and that should execute the tests for us. So that's the structure of the testing suite that we're using. Now, how we'll make this more clear, we'll add more tests to the same file and see how that functions. So now, what we'll do is we'll go to our file again. Let me remove this, and yeah, I will add a test for 5. Now, the factorial for 5 is 120. So that's, again, just to verify for people how we are doing the testing is we look at a test, we look at an output that we know is expected. So factorial 5 gives us 120, and that's something that we can calculate, and that does not need a lot of calculation. But what it helps us with is that it verifies that, oh, if you're testing for 3 and 5, we can assume that it would be good for 4 as well. But we will see the edge cases where it might be false, because sometimes you can successfully pass the tests, but your code might still be logically wrong. And that's something that we'll look at and see how the code functions as well. So this is what we are adding into our class. I'll paste this into the chat. And once we've done this, we will run our testing again. So we will again do the Python 3. So let's do Python, and then we call unit test. And this time I'll add a -v. So we'll see what that does for us in a second. And I'll again call the same file. So when I run this gives us that it ran test 3 and it ran test 5. And then it gives us a small it gives us more information about what it exactly ran. When it tests, then the file test factorial, then the class test factorial functions, and then the method test 3. So when you look at all these dots, these are basically the layers of the code that we are using here, like we use in Python modules. And it runs both of them, gives us an OK response, and tells us that it ran 2 tests and tells us that it was able to run it. So if you're able to add this new test and run the new test, could you give us a green tick again? Okay, I see a few green ticks. I'll give people a couple of minutes. Is there anyone who is having trouble or has any particular questions about what we have discussed so far? So if your tests run and you do not see the individual test file, okay, let's try to remove the -v. And this might be the thing. So this might be the output you're seeing. So the -v is basically for verbose, and -v is again a very standardized, usual sort of template for having something give us more information when we run something. So yeah, if you add the -v, that should give you those files. And this again is a general tip on Bash. Again, it does not equate for everything ever, but usually a minus and a small v will give you more information because it gives you the verbose information of what's running. So that's same with, say, if I'm doing a pip install, if I'm doing something else. And if I do a pip install matplotlib, it might just sort of take, say, 10 seconds, 20 seconds in the background and then give me matplotlib installed. But if I do a pip install matplotlib with a -v, it will show me the process as it's doing it. So that's the only difference. But as long as you're getting an OK response and your tests are running, it should be fine, because otherwise it would give you an error if your test was wrong. Okay, so I see a few green ticks. And I'm imagining if folks are not able to see it with the -v as well, that might be again a versioning thing or local setup thing. But I would imagine if you add the -v to your command, I'll paste the command again. So this should be your command, but if it's with Python, it should be this. And that should give you a similar output for both the files. And even without it, what is a good way to verify is that it does say ran 2 tests. So you know that it's running both of them. Now, okay, so now that we've added both of these files, let's go back into our Python and test how this function is working. So right now we've just been running the tests and not actually calling this function. So let's see, we go to Python 3, and then we do the similar import that we did before. So we do from mymath.factorial import factorial. We click enter, and then let's say test for 6. So when we do a factorial 6, it gives us 720, which should be the correct output. So factorial of 6 is 720. And that's something that we can just test that, okay, the factorials are working correctly here. Now, what we will also do is let's try a bigger number. So I go for 1080, and now 1080 is a big number. So in factorials, because you keep multiplying every consecutive number, they increase exponentially very quickly. Let's see if Python is able to calculate that for us. So I'll do factorial 1080 and I click enter, and I get this error. So there's a lot of noise here. There's a lot of traceback things. A few of these things might not look very familiar or might not look very readable. But what we are most interested in is the last line, which says recursion error, maximum recursion depth exceeded. And this is basically the behind the scenes traceback for Python, that why it threw that error. So this is essentially happening because if you look at the function, what we're doing here is we are doing a recursive call. So we pass in n, so n is the input that we have, and we pass it into the function. And then what we do is we subtract 1 from n and then keep multiplying it. So if it's 7, it will go 7, then it will go back out of the loop into 6, into 5, into 4, until it reaches 1 again. And once it gets there, it will give us the output. So because the function is recursive, it runs the call every time. Now Python has a limit where the recursion can only run 1,000 times. So 1,000-time recursion is a limit because, again, recursion as a practice in Python can be very useful for some functions, but say beyond 1,000 recursive calls, it gets inefficient, and there might be better ways to say execute your code. So Python does not allow us to do that. It says maximum recursions have been exceeded. Now, if I clear this, so, okay, let me just go out of that again, clear, and I do this, and then I do a factorial of, say, 999, that should hopefully run. Yeah, so that gives us a huge number. So that's the factorial of 999. When we go to 1,000, it might not. Yeah, so again, 1,000 is the limit. So it did the 1,000 recursions and gave an error. It can't run that. So if everyone has been able to run this function again and is getting this error, a similar error, could you please give us a green tick? Just a note on this error. So this might be exactly the same for people who are on Python 3.11, Python 3.12. It might look a little different if you are on an older Python. So this is from Python 3.12. I'll wait for folks to execute this. Okay, let's look at the chat. Okay, there's a question about, can I run a method inside a class individually? Yeah, as Alex mentioned, it depends on where you're running it from. And yes, you can run a method individually from a class, but again, if you are testing You could do that. You generally don't do that, but again, you sometimes want to isolate a test, you can do that. But I think for general calls for any methods in a class, they are a lot of the times individually executed. Right. So yeah, if you want to run only the unit, the test 3, I haven't done this, but we can try doing it. I think, yeah, as Steve says, if we just sort of add another dot to our call. So as I mentioned, when we are looking at those certain dot sort of syntax where it's going into the layers of Python, you can go pretty deep down that layer. You can also go into internal functions, which might not be relevant here, but I will quickly show that as well. So if we look at this, so this is the command that Steve pasted. Now I go Python 3 -m unit test, and then I'll also give it a -v. Tests.test factorial dot test factorial functions dot test3. So this is our class and the method that we want to run. And when we do this, it runs the exact test. Now I can also do this for test 5 and it will give us the same. But if I do say test 7, that gives us an error because there is no test 7 that exists in the class that we've defined. So I see the green text. So let's go ahead. Now we all see the error for 1080. So 1080 can't be calculated with this Python function. Now to fix that, we can change the code and see how to sort of, adapt the code to make sure that this function accounts for, say, less recursion. For that, what we will do is let's rewrite this function. We can keep the docstring same because we're still calculating a factorial. Now we'll say a factorial, we set the default value equal to 1, and we use a for loop. Okay, so the autocomplete is giving me that suggestion where we do for I in range, and then we go from 1 to n+1, n is the input that we're giving it. And then we go factorial equal to factorial into I. So we keep we keep looping it in a for loop. And then at the end of the for loop, when we get out of the loop, we want to return the updated value of the factorial. So this is a for loop in Python. If you've come across this before, I've written this function which gives us a factorial. Now, what we can do is instead of going into Python, testing, okay, what's the factorial of 3? What's the factorial of 4? What's the factorial of 5? Testing helps us test this exact function with the test that we wrote before. Because what we essentially did was we changed the logic of the code, but what we want is the same. So the input would still be an integer or a number that we want to calculate the factorial of, and the output will still be the same output that you have for a factorial. Now, what we will do is we will change this code, and then we will run this test factorial.py again. So let's go to that command. And when we do Python 3 -m unit test, and we do tests and test factorial.py, that should run the same tests, but this time it would run it over the new code, using the new code. So we do that, and it gives us an okay response. So that means that our tests are running okay now. And now what we can do is, I'll wait a second and just check if people have been able to update their code to the new code and been able to run the test again. I'll paste the new code in the chat. And then again, we're using same command for testing. So if you're able to do that, if you could give us a green tick, that would be helpful. Now this time we have not updated the tests themselves. we have updated the code and the test still run and tell us that that code is correctly executing at least for 3 and 5. If you also recall, that does not necessarily tell us that if this will work on 1080 yet, because it still might give us an error. It still might give us a different error or the same error because the test is still testing for 3 and 5. And when we pass 1080 into the factorial.py, we don't know what Python will give out to us when we haven't executed it. So this is kind of, again, we won't get into, say, the more complex or the more sort of sophisticated testing mechanisms. This is a unique one. So if we want to test a big value, that's say an edge case, for example, it's not a common case for this function particularly, but it's also not easy or straightforward to test via unit test. You can do it wherein you can look at what is the factorial of 1080, and then you can define a test. You can say test and then underscore 1080, and then you can give it the value that it should equate to. But that is not ideal because we want to do the testing for sort of basic fact checks that we can do quickly and just verify the correctness of the code. So for 1080, we'll have to do a separate calculation and then get into the tests, which you could do. It's not wrong, but there are more effective methods that you can use for testing things like that. And that again, when Alex earlier was talking about the different testing methodologies, the different ways to test, there are certain suites that help us do that. So when we look at mock testing, when we look at PyTest, when we look at all the sort of integration testings, those coming together help us test a lot of these cases. Or what if the value is too high? What if the value is too low? What if the value is a decimal? Things like that. For this case, we'll do a manual test and see if this helps us fix the recursion problem. I'll give people a few seconds. So if you can give us a green tick, if you've been able to update the code and run the test again successfully, just give us a green tick. If you're facing any issues or have any doubts, feel free to type it in the chat or give us a red cross. Okay, I see the green ticks. Now I'll clear my terminal again and let's go into Python. So we go Python 3 and I'm into the Python prompt. And now what I'll do is I will again import the factorial method. So I'll say from mymath.factorial import factorial. Again, if we want to do a quick sanity check, factorial of 6 still gives us 720. Factorial of 999, it gives us a big number. We're not verifying this. We're assuming that that's what we need. And let me just quickly clear the screen again. Okay, and now we'll test for factorial of 1080. So when we do 1080, that gives us another output, and it's different from the output we received before about the recursions. So now, again, what this does test is what the tests do for us are testing for 3 and 5, and assuming that this is the correct value, because mathematically, we know that this is how the factorial should look like. We can assume that this value is correct. But again, that's a tricky test because when you're testing for things that you do not necessarily know the output for, you have to trust some level of automation, some level of calculation, and you have to be aware of the different pitfalls of certain calculations. So I'll give you an example here, which we won't solve. But for example, if I do that import again, and now instead of 1080, I go for say 2000, it gives us an error. So now this is a different error where it's a value error. And here, Python basically cannot process that because we are exceeding the limit of 4300 digits. So the factorial of 2000 is exceeding that length of digits. It still does not tell us anything about the logic, but we know that, okay, that's the limitation of this code, where it can only run factorials up to a certain value. It might be somewhere around, say, 1200, 1300, 1400. We haven't tested for that yet. But we know that it is not testing for a bigger value. So higher than this, you can safely assume that this function, this factorial function that we've defined would not run or would not give us the correct output. This is also a good way to kind of do the elimination testing where because you know that these are the certain errors, you can also define, say, in your docstring, you can define in your function that this is the scope of your function. So you can test from 1 until, say, below 1,000, below 1,200 successfully with this function. So a user knows that, okay, this is the ideal test range for the function itself. Now, if everyone has been able to successfully run this and they're not getting an error for factorial of 1080, can you give us a green tick again? Okay. Now let's quickly just try to see when tests fail, what happens. So here, for example, if we say the factorial of 5 and we give it the output 10. Now we know that the factorial of 5 is not 10. This is again kind of like testing by negation in a way, where I know that the output should not be 10. But say I enter 10 and then I try to run the test again. So yeah, so this is the command for running the test. I run this, and now this runs the first test, which says test 3 is okay, because the factorial of 3 is 6, and that's correct. But for the second test, it gives us an error and it says fail. So this is failing because when the unit test framework executes this function, it gets an output of 120, but we have told it that it should expect an output of 10. And here it tells us assertion error, 120 is not equal to 10. And it says it ran 2 tests and 1 test failed. So this is basically testing by failure. In a sense, we are checking that this function is working correctly, that the test is working correctly. So if you want to quickly run this, you're welcome to, and you can give us a green tick, but that's just to demonstrate that, oh, the tests themselves are also limited by what information you give to it. So if you have a long logic and you give it if you've got a wrong logic and you give it a wrong answer, those might be correct when you have, say, defined a function which gives you the factorial of 5 as 20, and you write the same test. That's kind of just adding to that bias, and it's not checking the logic itself. But for, say, simpler things like this, where we know the factorial is being correctly being calculated, it helps us test both ways, that the tests are right and the code is right. Now, if we have done all of this, we can move ahead and do another testing for errors. So far we have this file, which is the factorial function. We have redefined how the factorial is calculated. So using a for loop instead of the recursion. And we have this tests file where we have 2 tests, a test underscore 3 and test underscore 5, which are doing the unit testing for us. Now, let's again go into our Python and let's give it, let's give it another output. So let's call, so we've imported the factorial again, and let's give it factorial of -1. So now a factorial of negative numbers is undefined. We'll run this and we'll see what the function gives us. Now, if I run factorial of -1, it gives me 1, which is the wrong output. And we know that by default, but the function does not have any checks for that, where it just gives us 1. It does not tell us why or how, but it gives us an output instead of an error. Say this would be similar if I give it -10, where again it gives us the output 1. So manually, if you want to check this, you could plug a value of -1 here and you will see the logic and how it's failing to give us 1 every time when it's a negative value. But what we want to do is, when it's a negative value, we want to tell the user that you cannot enter a negative value. And what we can do here is use Python to help us do that. So we can add another check. So if we say if n less than 0, and then we raise the value error. So yeah, okay, autocomplete is giving me that. Oh, okay, not that. So what we'll do is we'll add a value error and we'll say only use non-negative integers. Now we'll add this check right before we get into the function itself. So basically, if a user enters something that is negative, this function right here will raise an error and not calculate the factorial because that's not needed. So we'll add this on the top of our code, and then we'll see how it functions when we calculate the -1 factorial again. So I've pasted that into the chat, and again, for reference, this is in the material. Let me just quickly open that up. Now what we're doing here is we are just adding this, and then we will again do the same. We will call Python, we will do an import, and then we will try to get the factorial of -1. And that raises an error which tells us value error, only use non-negative integers. But this is an error that we are intentionally raising. We are telling the user that you cannot enter a negative number because that's not allowed in this function. So once we do this, it should raise this error and it should not allow us to enter negative numbers. So again, another check can be like we did before. We can do -10 and it should still give us the same error. So I will paste this in the chat. So we have a few minutes. This is where we're looking at. So this is the handling errors episode in the material. Now, if you've been able to successfully add this condition, this precondition which checks if the integer is positive and able to run it, can you give us a green tick? Okay. I see a few green ticks. Great. Now what we can also do is we can add a test for the same thing. Let me quit my Python prompt. And what I'll do here is I'll say define, and we'll test for negative. We'll pass the number, and this is the value that we want to raise. So this is the test that we've defined for a negative value, which is testing for an exception instead of the actual output that we want. This is intentionally that we know that an error should be raised when we give it a negative value. So we say define test negative. So that's the name of our method. We pass the value here, self, and then we say with self dot assert raises value error. So if you have a negative value, it should give you value error, and we have given it factorial -1. So it's the same error that should give us the value for any negative integer that would be for -1, because that's the lowest negative integer that we know of. So we add this test, and now when we run the tests, we should also be able to see how this function is working with a negative number. So I'll clear the feedback. And then first I've added this function, which is test negative. So this is the method that we've added to our testing suite. And then we will run our tests again. So we do a Python -m unit test, -v for verbose, and then we run this file. And when we run this, it says ran 3 tests in 0 seconds, and it tested test 3, test 5, and it also tested for test negative. Now here, again, if we wanted to check for failure, what we can do is we can run this again and it will fail this, because here what's happening is if we are equating it with factorial of 2, that is not a negative number and it's not giving us the expected output. So the error, so this is kind of layered in the sense that tests have an error themselves. This is not where we want to see the error. the test should be running okay. The error should be raised when we run the Python. So this value error means that the test is not running correctly, where it's saying assertion error, value error not raised. So the expected error is not raised here. And that's just a demonstration that when we test for -1, it is checking for negative numbers correctly. So I run this again, and I correct this to factorial of -1, and that gives us the expected output. So if you're able to add this test, and if you've been able to run the tests again, could you give us a green tick again, please? Okay, I see a few green ticks. I'll wait a couple of seconds. Amazing. Okay, so I think that's the end of the material. So